are looking at today is what we call central angles. We are going to define central angles. And look at the relationship that central angles have to what we call their intercepted arcs. I'm going to kind of paraphrase this objective here. So looking at how central angles relate to their intercepted arcs. And then finally, that's the main objective. Then we'll look at some theorems that have to do with chords here at the end. Main objective is to look at central angles and their intercepted arcs. Okay, we're going to start with our big, nice circle. We know that the center of the circle is in the middle. Let's call that C for center. A central angle is an angle whose vertex is at the center of the circle. This is an angle whose vertex is at the center of a circle. To me, it looks like a Trivial Pursuit pie piece. Okay, a central angle is an angle whose vertex is at the center of the circle. The portion of the circle that is in between the rays of the angle is the intercepted arc. There are a couple different types of arcs that we will talk about today. We have a minor arc. This is an arc whose measure is less than 180 degrees. So the red intercepted arc in your picture, that would be a minor arc because its measure is less than 180 degrees. And then we have a major arc whose measure is greater than 180 degrees. So back in our circle, the portion of the circle that is not intercepted by that angle, that would be considered a major arc because its measure is greater than 180 degrees. What about an arc that's equal to 180 degrees? The arc.
Oh.
What would the arc be? Well, let me ask you this. How many degrees are in a circle? Okay, so 180 degrees is half. What do you call half a circle? Come on. Half a circle? Semicircle? Oh.
Too easy.
Okay. Semicircle that has a measure of 180 degrees.
I'm lost.
All right, one thing that I want to mention, and we'll get some practice with this here in a minute. When you name a minor arc, you use 2 letters. When you name a major arc, you are going to use 3 letters. Okay, what we are going to look at now is finding the measure of each arc in circle. That should not be circle M, that should be circle R because we name circles based on its center point. So that is named incorrectly. This should be circle R. Now, one thing that I haven't told you is how the measure of the central angles relate to the measure of its intercepted arc. Do you have any idea how the measure of angle NRM, which is 80 degrees, how does that relate to the measure of arc MN? What? Okay, Mark said 2 times bigger or the same. Other ideas? The intercepted arc is the same as its central angle. So if angle NRM is 80 degrees, its intercepted arc, arc MN, which is what we're trying to find first, is also 80 degrees. Notice that that arc only has 2 letters in it. Its measure has to be less than 180 degrees, which it is. Next, we are asked to find the measure of arc MPM. MPN. What's the measure of that arc? 180?
100.
That certainly looks bigger than a semicircle to me. How is it 280?
Because the circle's 360 degrees and the central 80.
Exactly.
Oh.
We know that this part of the circle is 80 degrees, so the rest of it has to be 360 minus.
MP and then cut
Yeah.
through the middle.
No. It's always around the circle. Always around the outside of the circle. You follow the letters in the name around the circle. M, P, N. You have to go around the circle. All right, now I'm looking for the measure of arc PMN. So follow the letters around. P, then N, then N. What's the measure of that?
180.
Because it is a what?
Semicircle.
That is a semicircle. Next example is just having us identify whether the given arc is a major arc, a minor arc, or a semicircle. Right off the bat, the easiest thing to identify should be the minor arcs. Why?
This one is 180.
Not even looking at the picture, just looking at the names, Carrie. They only have 2 letters. So if you're looking at the very first one, arc AD, I know that if it's naming it with just 2 letters, that has to be a minor arc. And then if you want to go double check in your picture, you can look at arc AD. That is definitely smaller than 180 degrees. Same thing with BF. If it's naming it with just 2 letters, that has to be a minor arc. BF in your picture is definitely smaller than a semicircle. And finally, E, arc BE, named with 2 letters, that has to be a minor arc. All right, so we have the 3 minor arcs. Now let's go back. Let's look at B. Arc ADB. ADB. So I'm going from A, around to D, around to B. So we know if it has 3 letters in its name, it's either a major arc or a semicircle. Which is it?
Semicircle.
Semicircle. Very good. All right. For D, we have arc D, B, F. Is that a major arc or a semicircle? Hello? Major arc. It's bigger than 180 degrees. And finally, arc EBF. EBF. Major arc or semicircle? Ooh, look at it again. EBF, going from E to B to F. That is a semicircle. Two minor arcs are going to be congruent. If their corresponding chords are congruent. And I'll talk through each one of these kind of with the picture and how this is true. So take a look at our picture here. So we have chord AB and we have chord BC. Okay, those 2 chords, AB and BC. Notice those 2 chords are marked congruent. What that means is their corresponding arcs. So for example, arc AB, that is going to be congruent to arc BC. Okay? The corresponding arcs of those congruent chords are congruent, is what the first one says. Okay? The second one says if a diameter is perpendicular to a chord, then the diameter bisects the chord and its arc. Remind me what it means to bisect. Cut in half, good. Bisect means to cut in half. All right, so let's look at the picture. Here's what we have. If the diameter, so here's our diameter, if that diameter is perpendicular to a chord, so it's showing you that this diameter is perpendicular to a chord, what that means is it's going to cut that chord into 2 congruent parts. It's also going to cut this arc into 2 congruent parts. Okay? Because that diameter is going right through the center of that circle. Okay? All right. This next one is really just the converse of the last one. So if a chord is a perpendicular bisector, of another, then the first one is a diameter. So what this is saying is this. If you have 2 chords where one is perpendicular and bisecting the other one, that means this first one has to be a diameter. That would tell you that you know it's going through the center. Okay? All right, and the last one. Two chords are congruent if they are equidistant from the center. Two chords are congruent if they are equidistant from the center. So if you look at the picture, if these two chords, C, D, and A, B, are the same distance from the center point, so we're assuming that E, F, and E, G are the same length. That would mean that these two chords are congruent. Okay? All right, now all that's well and good, but our goal here is to be able to use those. So if you look at the first example, we are being asked to find the measure of arc KM. To find the measure of arc KM. So look at your picture. Arc KM is just that little arc right there. So our first goal here is going to have to be to find the value of x. So ideas on how we can do that. If we set 5x equal to 7x minus 16, and why are we doing that? Okay, Km is congruent to Mn. Now the question is, which of those theorems did you use? You can just say first, second, third, or fourth is fine. The second one, exactly. If that diameter is perpendicular to the chord, then it's splitting it in half, exactly. All right, so it's just a matter of solving. We can subtract 7x and divide by -2. So the value of x is 8, but remember our goal is to find the measure of arc KM. So how are we going to finish that up? Yep, we're going to take that value of the variable, plug it in. So 5 times 8 is 40 degrees. Find the length of QS. So look at your picture. Oh, where's Q? Q's the center. You might need that. Q's the center, so we're looking for that length, QS. If, that should say if the length of MN is 16, so fill in that the length of MN is 16, RT is 16, and NQ is 10, which is filled in your picture. So how can we find the length of QS knowing what we know? Okay, he said, can't we use Pythagorean theorem to first find the length of PQ because that will be the same as QS? Absolutely. So what we're focused on here is this little right triangle. Remember that MN is the 16. I know it kind of looks like where I put it that just PN is 16. But MN is 16. So if you take out that little right triangle, you have the hypotenuse is 8. We're looking for that side. What's this length of that third side? No. 8. MN, ladies and gentlemen, look at this. Some of you are like not paying attention. MN is 16. So what's PN?
It's 30, or not 30.
Half of 16, right, is 8. Yes? Using Pythagorean theorem, we can say 8 squared plus x squared equals 10 squared to solve for the value of x. So the length of PQ is 6, which means the length of QS also must be 6 because those are congruent.